Debunked. Will a black hole really eat the entire universe? Cosmic truth revealed. Hello, cosmic explorers, and welcome to Cosmic Enigma. Imagine a cosmic vacuum cleaner, an insatiable monster lurking in the dark, slowly but surely pulling everything into its inescapable grasp. For many, this is the terrifying image of a black hole, a devourer of worlds, destined to consume our entire universe. But this dramatic vision, while captivating, is fundamentally incorrect. The idea that a single black hole will eventually suck in all matter in the universe is one of the most persistent and dramatic misconceptions in astronomy. It sounds plausible, given their immense gravity, but the scientific reality is far more nuanced and, frankly, even more incredible. To understand why a single black hole cannot consume the entire universe, we must first grasp what black holes actually are. They are not empty voids or cosmic drainpipes, but incredibly dense objects formed from the collapsed remnants of massive stars. All that mass is squeezed into an infinitesimally small point called a singularity, creating an unimaginably powerful gravitational field. The defining characteristic of a black hole is its event horizon, a boundary in space-time, a theoretical point of no return. Once any matter or light crosses this boundary, the gravitational pull becomes so strong that escape is impossible. However, black holes only swallow objects that venture extremely close, specifically those that cross their event horizon. They are not cosmic vacuum cleaners actively drawing in distant matter. A black hole's gravitational pull is determined solely by its mass, just like our Sun or Earth. If our Sun miraculously transformed into a black hole of the same mass, Earth's orbit would remain entirely unchanged. Our planet would continue along its familiar path, though it would become profoundly dark and cold. The gravitational force exerted by the Sun turned black hole at Earth's distance would be precisely the same as that of the Sun itself. This demonstrates that a black hole's gravitational effects are localized. They are only overwhelmingly powerful in their immediate vicinity. Even the most massive black holes known in the universe possess event horizons that are minuscule when compared to the immense distances separating objects in space. For instance, a black hole with the mass of our Sun would have an event horizon extending only about 2 miles. For any star to be swallowed by a black hole, it would need to be aimed almost directly at it, a cosmic bullseye that happens only rarely over truly immense timescales. Furthermore, black holes, even supermassive ones, exhibit a form of self-regulation that prevents them from growing indefinitely and devouring entire galaxies, let alone the universe. As these colossal objects accrete matter, they also release tremendous amounts of radiation. This outgoing radiation heats and ionizes the surrounding gas and dust, making it increasingly difficult for that matter to cool down and fall into the black hole. This process effectively slows down the black hole's feeding rate, acting as a natural brake on their growth. Beyond the localized nature of black hole gravity, the sheer scale and dynamic evolution of the universe itself present insurmountable barriers to any single black hole consuming all matter. The cosmos is unimaginably vast. The observable universe alone spans a diameter of approximately 93 billion light-years. The space between galaxies, known as the intergalactic medium, is largely empty, containing only a sparse distribution of gas and dust. This immense emptiness means that matter is not densely packed in a way that would allow a black hole to easily accumulate it from vast distances. Moreover, the distribution of matter in the universe is not uniform. Galaxies are organized into a colossal network known as the cosmic web, consisting of long filaments of galaxies and clusters, separated by enormous, relatively empty voids. This intricate arrangement means that matter is already spread out across immense distances, forming structures that are far too large and diffuse for a single black hole to consolidate. Crucially, the universe is not static, it is actively expanding. This expansion is not merely continuing, but is actually accelerating. This acceleration implies a fundamental challenge to gravity's long-range pull. The very fabric of space-time is stretching, carrying galaxies further apart at an ever-increasing rate. This relentless expansion is the ultimate counterforce to any gravitational collapse on a cosmic scale. The driving force behind this accelerating expansion is a mysterious entity known as dark energy, which makes up approximately 68 to 70% of the universe's total energy and matter content. Unlike dark matter, which exerts a gravitational pull and helps hold galaxies together, dark energy acts as a repulsive force, effectively pushing galaxies apart on large scales. The direct implication of this accelerating expansion is profound. As objects in space become increasingly distant from one another, their likelihood of colliding with or being captured by a black hole diminishes significantly. The expansion ensures that on intergalactic scales, the gravitational pull of black holes, even supermassive ones, is overwhelmed by the relentless stretching of space itself. There is simply nothing to push all the matter of the universe into the black holes. To further solidify this understanding, it's helpful to address several other common misconceptions. Black holes are not cosmic vacuum cleaners. Their gravitational pull is identical to that of any other object of the same mass, only extreme up close. It is perfectly possible for objects, including stars and planets, to orbit black holes in stable trajectories, just as planets orbit stars. The supermassive black hole at the center of our own Milky Way galaxy, Sagittarius A star, provides a prime example. Countless stars orbit it without being swallowed. Furthermore, black holes are not literal holes or tunnels in the fabric of space-time, nor are they shortcuts to other dimensions or universes. They are incredibly dense, compact objects that dramatically warp space-time around them, but they remain physical entities. Lastly, black holes are not stationary. Like all celestial objects in the dynamic universe, black holes are mobile. They move through space, orbit other objects, and can even collide and merge with other black holes. The combined realities of localized gravity, the immense and ever-increasing distances between cosmic objects, and the accelerating expansion of the universe driven by dark energy definitively prevent any single black hole from consuming all matter. While black holes are fascinating and powerful localized phenomena, they are not the ultimate arbiters of the universe's fate. The grand destiny of the cosmos is instead determined by the delicate balance between the attractive force of gravity and the repulsive force of dark energy. Based on current observations of the accelerating expansion, the most widely accepted scientific theory for the universe's ultimate end is the Big Freeze, also known as heat death. In this scenario, the accelerating expansion continues indefinitely, causing galaxies to recede further and further from each other until they are beyond each other's observable horizons. Over truly immense timescales, stars would exhaust their fuel and burn out, leaving behind stellar remnants. Eventually, even black holes are theorized to slowly evaporate through a process known as Hawking radiation. The universe would then enter a dark era where all energy and heat would be uniformly distributed, resulting in a cold, dark, and utterly inert cosmos with no usable energy for any processes. Other theories for the universe's ultimate fate, such as the Big Crunch, where the universe collapses back on itself, and the Big Rip, where everything is torn apart, are now largely disfavored by observational evidence. The dramatic image of a single black hole inexorably consuming all matter in the universe is a captivating, yet scientifically unfounded, misconception. Black holes are not cosmic vacuum cleaners. Their immense gravitational pull is localized, affecting only objects that venture extremely close to their event horizons. More fundamentally, the universe itself is an unimaginably vast and dynamic entity, not only expanding, but doing so at an accelerating rate, driven by the mysterious force of dark energy. This relentless expansion ensures that on intergalactic scales, the gravitational pull of black holes is overwhelmed, pushing objects further apart and making cosmic collisions increasingly rare. The true scientific understanding of black holes and the universe's grand evolution is far more intricate and awe-inspiring than any sensationalized myth. The cosmos is a realm of profound complexity, governed by the interplay of gravity, dark energy, and the relentless expansion of space itself. This journey of scientific discovery transforms anxiety into inspiration, fostering a deeper, more nuanced appreciation for the magnificent and enduring cosmos.